uncertainty. When you talk about random variables, random variable Q, and we've said that it has values Q1 up to say Qn, and probabilities P1 up to Pn, we speak of a standard deviation, delta Q, as the uncertainty, the standard deviation. And how is that standard deviation defined? Well, you begin by making sure you know what is the expectation value of the, or the average value of this random variable, which we've defined last time. I think I put braces, but bar is kind of nice sometimes too, at least for random variables, and it's the sum of the pi times the qi's. The uncertainty is also some expectation value, and the expectation value of deviation. So the uncertainty square is the expectation value, sum over I, of deviations of the random variable from the mean. So you calculate the expected value of the difference of your random variable and the mean squared, and that is the square of the standard deviation. Now this is the definition, and it's a very nice definition because it makes a few things clear. For example, the left-hand side is delta Q squared, which means it's a positive number, and the right-hand side is also a positive number because you have probabilities times differences of quantities squared. So this is all greater than equal than 0. And moreover, you can actually say the following. If the uncertainty or the standard deviation is 0, the random variable is not that random, because if this whole thing is 0, this delta Q squared must be 0, and this must be 0. But each term here is positive, so each term must be 0, because if any one of them was not equal to 0, you would get a non-zero contribution. So any possible Qi that must have a Pi different from 0 must be equal to Q bar. So if delta Q is equal to 0, Qi is equal to Q, and it's not random anymore. Okay. Now we can simplify this expression. And do the following. By simplifying, I mean expand the right-hand side. So sum over I, Pi, Qi squared minus 2 sum over I, Pi, Qi, Q bar plus sum over I, Pi, Q bar squared. This kind of thing shows up all the time, shows up in quantum mechanics as well, as we'll see in a second. And you need to be able to see what's happening. Here, you're having the expectation value of Qi squared. That's the definition of the bar of some variable. You multiply the variable by its probability that it occurs. What is this? This is a little more funny. First, you should know that Q bar is a number, so it can go out. So it's minus 2 q bar, and then all that is left is this, but that's another q bar, so it's another q bar. And here, you take this one out because it's a number, and the sum of the probabilities is 1, so it's q bar squared as well. And it always comes out that way. This minus 2 q bar squared plus q bar squared, so at the end, delta q, it's another famous property, is the mean of the square minus the square of the mean. And from this, since this is greater or equal than 0, you always conclude that the mean of the square is always bigger than the maybe I shouldn't have the I here. I think it's a random variable q squared. So the mean, the square of this is greater or equal than q bar squared. Okay. Well, what happens in quantum mechanics? In quantum mechanics, let me give you the definition and couple of ways of writing it. So here comes the definition. It's inspired by this thing. So in quantum mechanics, Hermitian operator Q will define the uncertainty of Q in the state psi, all squared, as the expectation value of q squared minus the expectation value of q squared. Those are things that you know in quantum mechanics how you're supposed to compute. Because you know what an expectation value is in any state psi. You do psi star, the operator psi, and here you do this thing. So it's all clear. So it's a perfectly good definition. Maybe it doesn't give you too much insight yet, but let me say two things, and we'll leave them to complete for next time, which is claim 1, that delta q squared psi can be written as the expectation value of q minus absolute expectation value of q squared, like that. Look, it looks funny, and we'll elaborate this, but the first claim is that this is a possible rewriting. You can write this uncertainty as a single expectation value. This is the analog of this equation in quantum mechanics. Claim 2 is that another rewriting, delta q squared on psi, can be rewritten as this. I will make this an integral into infinity q minus q psi. Look at that. You act on psi with the operator q and multiplication by the expectation value of q. This is an operator, this is a number multiplying psi. You can act with this on the wave function. You can square it and then integrate. And that is also the uncertainty. We'll show these two things next time and show one more thing, that the uncertainty vanishes if and only if the state is an eigenstate of Q. So if the state that you're looking for is an eigenstate of Q, you have no uncertainty. And if you have no uncertainty, the state must be an eigenstate of Q. So those all things will come from these claims that we'll understand next time.